Shifting theorem. So actually shifting theorem is given by a statement. So this theorem states that if x of t is equals to 0, okay, if x of t is equals to 0 for t less than 0, x of t has z transform of x of z, then so the statement is saying 1, z transform of x of t minus nt, capital T, small t minus n capital T is equals to z power minus n x of z. And the second one is saying z transform of x of t plus nt is z power n into x of z minus sigma k is equals to 0 to n minus 1 x of kt z power minus k. So these are the equations given for shifting theorem. So it is stated that shifting theorem means these are the two. T minus nt should be z power minus n into x of z. T plus nt should be z power n into x of z minus sigma k is equals to 0 to n minus 1 x of kt z power minus k. So we need to prove this. So how to prove? So the proof. First let us prove the first one. So the first one, okay, z of x of t minus nt. How can I write it? Usually z of x of t is what? Sigma k is equals to 0 to infinity x of k z power minus k, right? So instead of t we got kt, nt will be nt, right? X of kt, x of kt, t minus nt, so kt minus nt, z power minus k. So general formula only we wrote, but instead of kt we wrote kt minus nt. The reason why we wrote kt minus nt is because it is t minus nt, so we wrote kt minus nt. Okay, so t minus nt, so kt became kt minus nt. Okay, now so I can write this as sigma k is equals to 0 to infinity x of kt minus nt z power minus k, and I am doing z power n, z power minus n extra multiplication because I am want k minus n, so n is missing here, so that's why I multiplied z power n with z power minus n. So this is equals to sigma k is equals to 0 to infinity x of k minus n t z power minus k minus n. It means minus into minus plus n is the one I took. It means plus n came inside, so that means z power minus n is also. Okay, so now it is x of k minus nt z power minus k minus n. So again this is the original equation, sigma k is equals to 0 to infinity x of kt, because what is our original formula? X of z is equals to sigma k is equals to 0 to infinity x of kt z power minus k. Instead of k, k minus n is there. Instead of k, k minus n is there. So overall equation can be x of z. So this whole equation I can refer it as capital X of z, z power minus n. That is the solution. So you can see kt minus nt, kt minus nt. So that's why I multiplied z power n with z power minus n. So I brought positive inside, so I took it as negative. So negative will be positive only. So when positive came inside, the negative is outside. So this overall equation is in the standard form, k minus n, k minus n. So I can simply write this whole term as capital X of z with the leftover multiplier. So this is that. So with that I am done proving the first statement. Now the second statement, right? So coming to the second statement, it is talking about t plus nt. So it is talking about z transform of x of t plus n capital T, right? So this is equals to sigma k is equals to 0 to infinity. This is what we write as a formula, right? So the same thing I am writing, kt plus nt z power minus k. So here this is k plus n. So here also I want k plus. So to bring k plus n, I am writing kt plus nt z power minus k. I wrote the whole equation, and I am writing z power n, z power minus n multipliers. So now I want is positive n. Here positive n means I should bring negative n inside. So I am writing it as sigma k is equals to 0 to infinity x of k plus nt z power minus k plus n. Minus into plus is minus. It means z power minus n is brought inside. So that means positive should be outside. Now the positive z power n is outside, but here we can see that k plus n, k plus n. So k plus n means beyond k. So beyond k, initially it is k minus n, means less than k. So this sigma is perfect. But here k plus n means beyond k the equation is going. So I am referring k plus n as m. So if k is equals to 0, 0 plus n is equals to m, means m is from n to infinity. M is from n to infinity. So this equation becomes sigma k is equals to 0 to infinity. So m is from n to infinity means 0 to n minus 1 terms are missing, right? Because you can see the equation is talking about n to infinity, means 0 to n minus 1, the terms are missing. So to get that terms to this equation, we are writing x of k plus n into t z power minus of k plus n. The same equation I wrote it here, okay? Plus sigma k is equals to 0 to n minus 1, because for me n minus n minor terms are missing. So that's the reason I wrote k n minus 1 x of kt z power minus k. So I added, means I should even subtract also. So k is equals to 0 to n minus 1 x of kt z power minus k. Okay, but we should remember that the whole equation is multiplied with z power n. So z power n is there in the equation. Okay, so we should remember that z power n is still there. So I wrote it here. Okay, so now from this equation I can say this as z power n into sigma k m is equals to 0 n to infinity x of mt z power minus m plus sigma k is equals to 0 to infinity x of kt z power minus k. So I am taking these two minus sigma k is equals to 0 to n minus 1. This is also 0 to n minus 1, sorry, n minus 1 x of kt z power minus k. N to infinity 0 to n minus 1. So this one and this one, both I am writing them as sigma k is equals to 0 to infinity. Okay, so total I mixed up 0 to infinity x of, let me write it as m also, okay, anything is fine, mt. For you not to confuse, I am writing it like that. Okay, z power minus m minus sigma k is equals to 0 to n minus 1 x of kt z power minus k. So this equation is x of z. So z power n into x of z minus sigma k is equals to 0 to n minus 1 x of kt z power minus k. So this is the second statement. So shifting theorem is of two statements. The first statement is talking about t minus nt, and the second statement is talking about t plus nt. When I wrote t minus nt, the equation is direct. But when I wrote t plus nt, it is in terms of positive, beyond k. So I named beyond k as m, but m is talking from n to infinity only, but it is not talking about 0 to n minus 1. So I added 0 to n minus 1. As I added, I subtracted 0 to n minus 1 also. So now this 0 to n minus 1, and this equation is n to infinity. N to infinity, 0 to n minus 1. Both will add on to frame m from 0 to infinity. So I got a standard one with the subtracted one. Standard one I wrote standard equation, subtracted one I wrote it here. The multiplier is there. So this is the proof for shifting theorem. Okay, so our next concept is final value theorem. Okay, so final value theorem is also given with a statement already. So the statement is there. So what is that? Final value theorem. So according to final value theorem, what is given? Suppose x of k is equals to 0 for k less than 0 has a z transform x of z, and that all the poles of x of z lie inside the unit circle with the possible exception of the simple pole. Then final value k approaches infinity is limit k tends to infinity, x of k is equals to limit z tends to 1, 1 minus z inverse x of z. So this is the statement for final value theorem. So in the exam, I will give the statement. So no need to worry. I will give everything. You should prove it. Even shifting theorem, I will give the whole statement. So this whole thing I will give. You should start from the proof only. So now we need to prove the final value theorem. So to prove the final value theorem, so to start the proof, first we are taking our standard equation z of x of k. So what is z of x of k? So our z x of k is sigma k is equals to 0 to infinity x of k z power minus k, which is equals to capital X of z. Similarly, z of x of k minus 1, which is equals to sigma k is equals to 0 to infinity x of k minus 1 z power minus k, which is equals to z power minus 1 x of z. Okay, this thing we said by multiplication by a power k. Okay, so there we got this. The same thing I substituted here. Okay, so now I am going to subtract these two equations. So this is my equation 1 and this is my equation 2. I am going to subtract 1 minus 2. So when I am going to subtract x of z minus is these two. Okay, so here sigma k is equals to 0 to infinity x of k z power minus k minus sigma k is equals to 0 to infinity x of k minus 1 z power minus k. Okay, so this is equals to x of z minus z inverse x of z. According to formula, there is a limit z tends to 1. Okay, so I am applying limit. So I will say apply limit because the question is saying, so no need to worry. So limit z tends to 1 on both sides. So this can remind you in the exam. The question itself can remind you that you should apply limit z tends to 1. So now what happens? Limit z tends to 1, sigma k is equals to 0 to infinity x of k z power minus k minus sigma k is equals to 0 to infinity x of k minus 1 z power minus k is equals to limit z tends to 1 x of z into 1 minus z inverse. Okay, so can you see limit z tends to 1 minus z inverse x of z, limit z tends to 1 minus z inverse into x of z. So this term, so they matched. So now our target is to bring the right side term. So left is done. Now we need to concentrate on the right thing. So this is our right thing. So now let us apply limit z tends to 1 in the sigma in the equation. So limit z tends to 1. So I applied sigma k is equals to 0. So x of 0 z power minus 0 is x of 0 plus plus let me say first 0 plus x of 1 x of 1. So z is what if k is equals to x of 1 z power minus 1. So x of 1 z power minus 1 plus we are having x of k is equals to 2. So like that we are going to substitute the terms. So when you are substituting the terms, we are further moving it like x of 2 z power minus 2 minus. So let's say plus so on for this, then minus sigma x of 0, right, means minus 1 x of minus 1 z power minus 1 z power 0 minus x of 1, because 1 minus 1 x of 0 z power minus 1 minus x of 1 z power minus 2 minus so on, which is equals to right side equation. Okay, let's not waste the time. So just right side equation, same equation substitute. Now z I am substituting. Z power 1 means 1 power 1, 1 power 1, 1 power 1, 1 power 1, all things, whatever it is, all are 1 power 1s. So next what is the leftover equation? X of 0 plus x of 1 plus x of 2 plus so on plus x of infinity, right? That is the term. Then here minus, I am going to get x of minus 1 minus x of 0 minus x of 1 minus so on until minus x of infinity minus 1. Okay, so now all these terms are getting cancelled. So all the terms gets cancelled with infinity minus 1. So everything gets cancelled and only x of infinity is left, which is equals to r. So finally we are left with only x of infinity, but x of infinity is equals to this. So x of infinity, I am writing it as limit k tends to infinity x of k is equals to r. Let me write the equation again, it's not clear here. So what I am writing, limit k tends to infinity, because I got x of infinity. So x of infinity I am terming it as x of k to look it official. So x of k with the limit k tends to infinity is equals to limit z tends to 1 minus z power minus 1 into x of z. So this is the equation. Okay, so we proved. So they want this, so we got this. So this is final value theorem. So final value theorem and shifting theorem. So these two theorems, statements will be given and you are supposed to solve them according to the statement. So observe, when you're preparing, observe the statement. So some things what to do will be given in the question itself. You should be little more smart to see where which is the hidden answer for this. Okay, so these are shifting theorem and the final value theorem.